Hello.
Unmute
Please go ahead, you
yourself.
are
We are
audible.
not able to hear your sound.
Sir, no, he is unmuted. I can hear him.
Hello. Hello, sir.
हॅलो. हा सर, ते OnePlus ला आहे ना, OnePlus CH-2661 ला माईक अलाउड करा.
Hello.
हॅलो. हॅलो, आवाज येतो का सर?
हो सर, आवाज येतोय तुमचा.
पण ते इको येतोय. ते OnePlus माझं एक आहे ना, OnePlus
सर 2 डिव्हाइस
CPH.
असतील ना तर एकच डिव्हाइस वरती करू शकाल तुम्ही. दुसरा डिव्हाइस
हो.
जवळ असेल तर चालणार
नाही,
नाही.
एका
इको होईल.
डिव्हाइसला म्यूट करा.
हो.
एका डिव्हाइसला म्यूट करा. सर, ऍडमिन म्हणून आहे ते तुमचं आहे का, तांबडे सर? अजून कुठला डिव्हाइस आहे म्हणालात तुमचा?
OnePlus म्हणतायत
OnePlus
का?
CPH.
OnePlus, हा.
अच्छा, शेअर कुठून करणार आहात, म्हणजे को-होस्ट करायला?
तांबडे सर, तुमचा शेअरिंग डिव्हाइस कोणता आहे?
तांबडे सर, आवाज येतोय का आमचा?
आवाज येतोय. फक्त काय करा, जो माईक आहे ना याचा अलाउड करा मला.
नाव सांगा.
OnePlus CPH-2661 आणि शेअरिंग आहे त्याच्यावरच ठेवायचं.
आहे मॅडम,
तो
खाली आहे.
तुम्हाला अनम्यूट करायला सांगतोय.
हा, OnePlus CPH.
प्रॉब्लेम नाही येणार.
हॅलो, आता येतो का आवाज?
येस सर, यू ऑडिबल.
ओके.
शॅल वी स्टार्ट?
या.
झालाय का
Okay.
प्रॉब्लेम सॉल्व, तांबडे सर?
Yes.
हो.
Yes. Okay. Let's start.
Good evening, everyone. Good evening, all. So today we are going to start with the third session. Previously we had 2 sessions on it was on mathematical methods in physics by Dr. Shri Krishna Gaikwad sir, and the second session was taken by Professor Sunil Patil sir. So today we have an eminent teacher, Professor P.S. Tamde sir, and he'll be delivering NGP some numericals and some problems on harmonic motions, simple harmonic motions. So I request Kangodi sir to introduce the today's speaker. So what do you?
Okay. Good evening, everyone. All the participants, teachers, and Rekha ma'am, Secretary IAPT. Today we are having with us Dr. Popat S. Tamde sir. His educational qualification is MSc, PhD in physics. At present, he is working as an associate professor and research guide in physics, and also shoulders the responsibility of IQAC coordinator of Professor Ramkrishna More Arts, Commerce, and Science College, Akurdi. Apart with this academician, he combines physics education research with experimental applied physics and nanotechnology. He specializes in enhancing undergraduate learning through computer simulations, spreadsheets, and interactive tools. He has created so many such tools, useful tools for teacher, and lot many e-content based upon that type of tools is available on his YouTube channel and the internet too. He developed resources. Sorry. He developed resources for quantum mechanics, electrostatics, wave function, and charged particle motion. He also recently he concentrates on photocatalysis for wastewater treatment using different types of nanomaterials. Uh, his present research is dye-sensitized solar cells with both natural pigment and the sensitive dyes, synthetic dyes. Uh, as an outreach, he received an outstanding paper award for research on computer simulations in physics education at several locations. He has been honored with the Deepastamba Award for contributions to educational services in Maharashtra, and has co-authored several textbooks on atomic and molecular physics, electricity and magnetism, computational physics, and so many. Also, he has prepared some study materials for the different types of competitive examinations too. He has published 13 research papers from applied studies on degradation and solar cell to pedagogical papers on visualization techniques. He employs both theoretical and experimental approaches in his research alongside evaluating educational effectiveness. And overall teaching experience, almost 33 years teaching experience holds at his name. And he is one of the very distinguished speaker in the field of physics in the University of Pune. So I once again welcome today's speaker and all the participants and request him please start his session. Over to you, Tamde sir.
Thank you very much, and good evening to everyone here. I especially thank uh, Dr. Rekha Ghorpade Madam, Professor Kangude, and Professor Shashikant Shinde sir for giving me this opportunity to present here some topics on physics. So today I am covering oscillations. So here, so is it visible?
Yes, sir.
Yes, yes, yes.
Yes, sir. Yes.
Okay. So all participants here. Now we will discuss here simple harmonic oscillations. So these are general topics we discuss in simple harmonic motion, equilibrium, in which what is stable equilibrium, unstable equilibrium, oscillatory motion, spring mass system, then simple harmonic motion, displacement and velocity in simple harmonic motion, what is periodic time, what is frequency of oscillations, displacement and acceleration graphs, energy of simple harmonic motions, and other topics also. So we will mostly restrict on oscillatory motion, spring mass system here. Now, before going to oscillatory motion, we must know equilibrium. So the body is said to be in equilibrium at a point when the net force acting on the body at that point is zero. Means suppose this is body and it is at rest and no force acting on the body. So this position, it is called equilibrium position. Now, that equilibrium has three types: stable equilibrium, unstable equilibrium, and neutral equilibrium. Now, these equilibria are classified on the basis of displacement of body from equilibrium position. So if we displace body slightly from equilibrium position, we know at equilibrium position, net force acting on the body is zero. When we slightly displace body from equilibrium position, what happens? What type of motion occurs there? Depending on that, we have stable equilibrium, unstable equilibrium, or neutral equilibrium. First, we will consider what is stable equilibrium. Suppose we have bowl, and at the base of bowl, we have placed one ball. Now, if the ball is at rest, net force acting on the ball, that is force, is equal to zero, and it will remain at rest. So this position is equilibrium position. But if we slightly displace ball along the surface of inner surface of that ball, and if we release ball from that position, so what happens? This ball goes to some height. So we have applied energy to that ball. That's why it goes to that height. And if we release that ball from that position, so if we see, when we displace ball away from equilibrium position and we release it, so we get some bounded motion about the equilibrium position. So such a equilibrium is called stable equilibrium. So if a slight displacement of particle from its equilibrium position results only in small bounded motion about the point of equilibrium, then it is said to be stable equilibrium. Now, we know if we raise body from surface to some height, we know mgh, it is potential energy at that point. Depending on that, we are raising this body along this surface. So you may get graph like this, graph of potential energy. So graph of potential energy, generally it is parabolic shape. So V is proportional to x square here. Now this is potential energy versus position graph. Means here, if it is see shape of that ball, on the basis of that, using this mgh, h is height of the ball from the ground, we get curve like this. V is proportional to x square here. Now, when we displace ball from equilibrium position or body from equilibrium position, force acts on the body. Now, if we take any point A, now this is curve P versus X. So at point A, it is on the right side. Suppose it is at X from equilibrium position, horizontal distance, it is X from equilibrium position. Now we can draw tangent to that graph at point A. Now if we find slope of that tangent, so slope is dv by dx. Means here, this is dx and this is dv. And if we see here, slope is positive. And if we have conservative system, force is negative gradient of the slope for conservative system. Now our slope is positive. So this quantity dv by dx is positive. So force is negative. Negative means force is not negative. Its direction is opposite. Force is not negative. Its direction is opposite. So in simple harmonic motion, when there is negative sign to any quantity, means its direction is opposite to x-axis. So here force is opposite to displacement. Means force is towards equilibrium position. If we take, so force is negative, that is directed towards equilibrium position. Even if we take point on this side, on left side of the graph, here we can draw tangent. So displacement here we take minus x. Minus x means along negative x-axis. If we draw tangent here, now slope of this tangent, it is negative. So dv by dx, its value is negative. So this term, it is negative. F is negative of negative value. So force is positive. Means force is along positive x-axis. Means it is towards equilibrium position. It is towards equilibrium position. So what happens? Here, if we see force is towards equilibrium position, here also force is towards equilibrium position. So on both sides, when body is displaced on either x positive x side or negative x side, force acts towards equilibrium position, and such a motion, it is called oscillatory motion. Now let us, and this equilibrium is called stable equilibrium. This point, it is called stable equilibrium. Now suppose we take bowl like this, and if we gently place ball on the top of that bowl, it may remain at rest if we gently place. So force acting on this point is 0. So this point, it is equilibrium point or equilibrium position. But if we slightly display ball from equilibrium position and if we release it, what will happen? It will go away from the equilibrium position. So this is equilibrium position. The ball will go away from equilibrium position. So if a slight displacement of the particle from its equilibrium position results unbounded motion, because it will never return towards equilibrium position again, it will go away from the equilibrium position. Then such a equilibrium, it is called unstable equilibrium. It is called unstable equilibrium. So there is no bounded motion. So if we see in terms of potential energy graph, now potential energy at the equilibrium position, it will be large. And on both sides, since it is slope, potential energy goes on decreasing. So between minus A and plus A positions, we have this potential energy graph. And we place body at equilibrium position here, means its potential energy will be maximum. And if we suppose display to point A, means we have displayed body to point A here. So here its potential energy will have some value. So if we draw tangent to that point, so displacement is x. If we draw tangent, and if we find slope of this tangent, now see, here slope, as Vx decreases, x increases. So slope will be negative here. And we know force is again minus dv by dx. So slope is negative, force is negative gradient of slope. So negative becomes positive. So force is along positive axis. So force is along positive axis means force is away from equilibrium position. If you see, force is away from equilibrium position. That's why body goes away from equilibrium position when we slightly displace body from equilibrium position. Similarly, if we take point on this side, what will happen? Now see here, this is the graph. Now if we find its slope, slope will be positive. Slope will be positive, and f is equal to minus of positive value, negative. So force is negative, displacement is minus x, force is negative. So it is again away from equilibrium position. So either we displace body on left side or right side and release it, it will go away from equilibrium position. So what happens in this case? Force is negative, that is directed away from equilibrium position. So there is no bounded motion, and such a equilibrium is called unstable equilibrium. Now, bounded motion is possible only when there is stable equilibrium. So what is oscillatory motion? First we will see periodic motion. What is periodic motion? Any motion that repeats itself after equal intervals of time is called periodic motion. If we take simple motion, particle is moving along circular path. So if we suppose we take point A here, body will go and again come at point A. Then again it will go and come again at point A. In each case, if we get same time t, then it is periodic motion. Now, in periodic motion, path is not important, but what is important? That path trace. So this is also periodic motion. So here, this is also periodic motion. The motion is repeating itself after equal intervals of time. So periodic motion, it is repeating itself after certain interval of time. Now, if an object in periodic motion moves back and forth over the same path, the motion is called oscillatory or vibratory. So here, if we take point, suppose A here, what happens? This body, it moves in this direction as well as in this direction at that point. While here, if we take here in circular motion, if we take point A, body always go in this direction. It never goes in this direction. So it is not to and fro motion here, but here it is to and fro motion about certain point. So this motion, it is oscillatory motion or vibratory motion. Now, both are periodic motions. Both are periodic motions. But what is the difference between oscillatory motion and periodic motion? So time required to complete round trip journey, it is called period. If period is large, then that motion is called oscillatory motion. But if period is very, very small, means in millisecond, microsecond, then it is called vibratory motion. So when oscillations are very fast, generally that motion is called vibratory motion. Now, oscillatory motion may be linear, means there is to and fro motion along straight line, or motion may be along curved path. So if we take point A here or point A here, in both cases there is to and fro motion about point A. But in first case, the path is linear path, while in second case, the path is curved path. So this first motion, it is called linear motion, and this is angular motion. This is angular motion. So we will consider linear motion here. An example of that, it is spring mass system. So suppose we take a spring, we attach a block of mass m to that spring, and other end of spring we fix here, and it is placed on smooth horizontal surface, very smooth horizontal surface. Now we can extend that spring by x. So x is displacement. This is called on positive side. So this is called extended mode. We can have compressed mode, means we can compress spring. So we will move mass in left side. So spring is compressed. This is called compressed mode. So if we extend spring, what happens? We are applying force on mass, and due to that, it is extended. So some potential energy, it is stored in the spring, and force here, it will act towards equilibrium position. When it is compressed again, the force will act towards equilibrium position. So when we release this spring, what will happen? It will start oscillating. That mass will start oscillating about equilibrium position. So this system, it is called spring mass system. And the equilibrium is stable equilibrium. So we know that for an ideal spring, the force is related to displacement by equation F is equal to minus kx. Means force is directly proportional to displacement and directed opposite to displacement. So this motion, it is called linear simple harmonic motion when force is proportional to displacement and directed opposite to displacement. So this is a linear simple harmonic motion. So here, this spring mass system, it is oscillating about some equilibrium position. So this is plus x, this is minus x. It will go up to certain distance on left side as well as on right side. Now we know when the force acting on the particle is directly proportional to the displacement and opposite in direction, the motion is said to be linear simple harmonic motion. So F is equal to minus k. And we know according to Newton's second law, force is equal to mass into acceleration. Now here x is displacement. So velocity it is dx by dt, rate of change of displacement, and acceleration it is d2x by dt square. Means it is dv by dt, rate of change of velocity. So force is mass into acceleration. Acceleration is d2x by dt square. So I can write the differential equation. So here we get m into d2x by dt square mass into acceleration is equal to minus kx. So I can take this kx on this side. So we get m d2x by dt square plus kx is equal to 0. If we divide throughout by m, so I will take this m here and call this k by m as omega square. Here, we take here omega square to avoid some complex numbers coming in the equation. You can take any constant, but we take constant in such a way that here we get square of that constant. So d2x by dt square plus omega square x is equal to 0. And we can, this is second order linear homogeneous differential equation. We can solve it easily. And if we solve, so here k is equal to, we have taken k by m is equal to omega square. So omega is equal to root of k by m. K is called force constant, m is mass of the mass attached to the spring. And solution of this differential equation, it is x is equal to a sine omega t plus phi. Now what is a here? What is omega here? What is phi here? So x is equal to a sine omega t plus phi. It is called equation of linear SHM. Now x gives you displacement of the mass from the equilibrium position at time t. So here x is displacement at time t from the equilibrium position. Now we will see one by one. Now omega t plus phi is called phase. Means here omega t plus phi, it is called phase because it will decide value of x at time t. And phi is called epoch of SHM. Epoch means the starting point of the system or starting point of whatever oscillations take place. Means here, suppose at t is equal to 0, I can take x is equal to a sine phi. And if phi is equal to 0, I will get x is equal to 0. Means oscillations will start from equilibrium position. So phi is called epoch of equilibrium position. It will give you initial position, that is position at time t equal to 0. Now see here, just we have taken here f is equal to minus kf. So f is equal to minus omega square x, k is equal to m omega square, omega is equal to k by m. And omega is called angular frequency. So x is equal to a sine omega t plus phi. A and phi are determined uniquely by position and velocity of the particle at time t equal to 0. If at t equal to 0, the particle is at x equal to 0, then phi will be equal to 0. If at t equal to 0, the particle is at extreme position, A is called amplitude of oscillation, then phi is equal to pi by 2. The phase of motion is the quantity omega t plus phi. Xt is periodic. X, that is function of time, is periodic and its value is the same after when we increase time omega t by 2 pi. So if we increase this omega t by 2 pi, means omega t plus 2 pi, we will get same position again. Now what is velocity? We know velocity is dx by dt. X is displacement. Velocity is rate of change of displacement. So if we differentiate this with respect to time, we will get a omega cos omega t plus phi. And we know sine square theta plus cos square theta is equal to 1. So I can write sine square theta plus equal to cos square theta is equal to 1 minus sine square theta. So cos theta is equal to root of 1 minus sine square theta. So using that, I can have V is equal to omega into square root of a square minus x square, where a is amplitude and x is position at time t. And so V is velocity at that time. The velocity is 0 at extreme positions and maximum at equilibrium position. So if we plot graph for phi is equal to pi by 2, so motion will start from extreme position and you will get displacement versus time graph like this. Now, so here, this position, this is time axis. This position means plus A. Again we get plus A here. Again we get plus A here. Again we get plus A here. So time difference between these two, same position. Again, with same phase or same direction. Time difference, it is called periodic time. Here also, see, if we take this position and this position, these are equilibrium positions. Here also, we have time t, and t is called periodic time. Now, this periodic time, we will get, if we convert this into omega t, we just multiply by omega. Omega is angular frequency. We get here pi by 2, pi, 3 pi by 2, 5 pi by 2, 3 pi, and so on. Now see difference between these two. What is difference between these two? This is omega t, because we have multiplied time by omega. So what is difference? So omega t is equal to 2 pi. So the period of oscillation is t is equal to 2 pi upon omega. And we know omega is equal to root of k by m. So if we take here, we get t is equal to 2 pi under root m by k. M by k. And this is now velocity graph. This is velocity graph. This equation. We know when sine omega t is 1, cos omega t is 0. So here, when here sine omega t is 1, so x is a, at that time velocity will be 0. And when sine omega t plus phi becomes 0, cos omega t plus phi becomes either plus 1 or minus 1. So here for pi by 2 it is plus 1. So C, maximum of position and maximum of velocity. Omega t, whatever time here, t dash suppose between two events, is equal to pi by 2. So if we take this omega t plus pi, here we have sine and here we have cosine. So phase difference between position and velocity is pi by 2. Position and velocity, it is pi by 2. So you can take phase difference between any 2 points having same x and same velocity. Everywhere you will get pi by 2. Everywhere you will get pi by 2. Now the period of simple harmonic motion is defined as the time taken by the oscillator to perform one complete oscillation. Means time required for round trip journey is called periodic time. Now from after every time t, the particle will have the same position, velocity as well as same direction. Means here this t is equal to 2 pi upon omega. Means suppose particle is moving along straight path between from x is equal to 0 to plus a and minus a. And suppose if we start measuring time from this position, so what happens? And now it is going in this direction. Now it will go towards plus a, then it will return here. So it will return at this position again. But this time for round trip journey, it is not periodic time, because when it is going along positive direction, this was direction. And now when it returns, this was direction. So what happens? We measure time for this. It will go up to plus a, it will return, it will go up to minus a, and then it will return here. Now sense of motion is same. Sense of motion is same. So this time is periodic time or period of oscillations. Now if we take here t is equal to 2 pi under root m by k, you will observe that t is proportional to m and t is inversely proportional to root of k. Means suppose we take first spring. This is first spring. And if we attach mass m and its force constant is suppose k1. And if we go on adding mass, period will go on increasing. But if we take second spring, and its force constant is k2, but same mass it attached, and if k1 is greater than k2, or I can say k2 is greater than k1. So k2 is greater than k1. So here periodic time is t1, here periodic time is t2. If we see this equation, t1 will be what? K2 is greater than k1. So T2 will be less than T2 will be less than T1. So here when spring constant increases, means when spring becomes strong, its periodic time becomes small, means it goes on decreasing with increasing K. So when strength of spring increases, its periodic time decreases. K depends on strength of spring. So if we take here graph of, suppose we plot graph of T versus M, you will get graph like this. parabolic graph, because t square is proportional to m. So graph is parabolic graph. Now frequency. The frequency represents the number of oscillations that the particle undergoes per unit time interval. Number of oscillations means number of round trip journeys in 1 second. Now we know definitely there is one oscillation in periodic time t. So simply we define f is equal to 1 upon omega. So omega by k. So f is equal to 1 upon 2 pi root of k by n. And units are cycles per second. And its unit, it is called hertz. That cycles per second, it is called hertz. So the frequency and period depend only on the mass of the particle and the force constant of the spring. It does not depend on amplitude of oscillations. So they do not depend on the parameters of motion like amplitude of oscillation. The frequency is larger for steeper spring, means large values of k, and decreases with increasing mass of the particle, while periodic time is opposite to that. Now displacement and acceleration. We know acceleration, if we take acceleration, it is d2x by dt square. So we know x is equal to a sine omega t plus phi. If we double differentiate this with respect to t, we will get a is equal to minus a omega square into sine omega t plus phi. So phase is same. This sine omega t plus phi is same. So if we plot graph, so suppose for pi by 2, we place graph, we draw graph. This is for displacement. It starts from plus a. At that time, what is acceleration? Acceleration will be negative. This is negative acceleration. So if we see maximum of acceleration and maximum of displacement, the phase difference between these two maxima, it is pi. So phase difference between x and acceleration, that is position or displacement and acceleration, it is pi, means they are opposite to each other. Means when displacement increases, force also increases, but in opposite direction. So this is about acceleration. So phase difference, it is pi. Now if we consider energy, the potential energy V is equal to 1/2 kx square, and kinetic energy is 1/2 mv square. But we have seen V is equal to omega square root a square minus x square. So if we use that, we will get k is equal to 1/2 m omega square in bracket a square minus x square. Now, if we add these two, total energy, that is kinetic energy plus potential energy, or E is equal to, if we simply add these two, because here k is equal to m omega square. So this is also equal to 1/2 m omega square x square. So 1/2 m omega square x square plus 1/2 m omega square a square minus 1/2 m omega square x square. So we get this key. Now if A is constant, means oscillator is oscillating with constant amplitude, then its energy is constant. That's why it is called conservative system. And in conservative system, force is negative gradient of the potential, because we get this V from this equation, F is equal to minus dV by dx. So this is a simple harmonic motion. It is conservative motion. Conservative motion means here energy is conserved. thus the total energy of the oscillator is constant. And M and omega, if we have same mass and same spring, M and omega are constants. So energy is proportional to what? Square of amplitude. Now, we will represent these two. I will take this 1/2 m omega square x square. This is potential energy and this is kinetic energy. Now, if we represent graphically, so this is just a brief summary of spring mass system. So when we extend this at time t is equal to 0, we will start from extreme position. So x is plus a, at the position velocity is 0, kinetic energy is 0, potential energy is 1/2 m omega square a square, and total energy is also 1/2 m omega square a square. So when we release from extreme position, when it comes to equilibrium position, time is 1/4 of periodic time, but position becomes 0. And we know velocity is omega under root a square minus x square. So it is plus or minus a omega at x is equal to 0. But here we take minus sign because it is moving along negative axis. Then it will go up to minus a, when period is t by time is t by 2. Its velocity becomes 0. So kinetic energy is 0. Potential energy becomes 1/2 m omega square a square, and total energy is this. When when it comes towards equilibrium position, again time is 3t by 4, x is 0, and now here velocity is plus a omega because here velocity it is along positive x-axis. So this is just summary of motion. Now, if we see graphical representation of kinetic energy and potential energy. Now, this is potential energy and this is kinetic energy. We know potential energy is 1/2 m omega square x square, and kinetic energy is 1/2 m omega square in bracket a square minus x square. So if we take x is equal to 0, we get kinetic energy 1/2 m omega square a square, that is maximum, and potential energy is 0. Total energy, that is addition of these two, and this is this blue line. This is horizontal line. It represents total energy and it is constant. And suppose we take particle. This is blue ball. It represents particle. Now it is displaced to equilibrium, extreme position, and we will release. When we release, ball from equilibrium position, it will move between plus a and minus a. It will pass through equilibrium position. Now, if you see, when particle is moving along straight line through 0 up to plus a and minus a, you will observe that its potential, when particle goes away from equilibrium position, its potential energy goes on increasing while kinetic energy goes on decreasing. And when we go towards equilibrium position, potential energy goes on decreasing and kinetic energy goes on increasing. But total energy remains constant. Now, if you see carefully the motion, you will observe when particle is at equilibrium position, its speed is large. because its kinetic energy is large. And particle goes away from equilibrium position towards extreme position. Its velocity goes on decreasing. Kinetic energy goes on decreasing. And at extreme position, either at plus A or at minus A, velocity becomes zero. Velocity becomes zero. Kinetic energy becomes zero. And we know when velocity is zero, kinetic energy is zero, we say that body is at rest, means the body stops. So what happens here? At x is equal to plus A or at x is equal to minus A, when body comes at that position, it stops there. But it will stop for an instant. Instant means it is not for 1 second or 2 seconds. Instant means it is very small time. So plus A or minus A, these are called instantaneous stops. Means momentarily it will stop and it will immediately return. So plus A and minus A, these are called instantaneous stops. And if we see at equilibrium position, it goes fast, either along this direction or along this direction. Now see, if we see potential energy curve and kinetic energy curve, these two curves cross each other at this point and at this point. Means kinetic energy and potential energy are equal at that point. So if we take that point, it is either A upon root 2 or minus A upon root 2. You can find this by simply equating this 1/2 m omega square x1 square is equal to 1/2 m omega square a square minus x1 square. X1 is position at which these two are equal. And if we find this, you will get 2x1 square is equal to a square from this. So x1 square is equal to a square by 2. So x1 is equal to plus or minus a upon root 2. So plus a upon root 2 or minus a upon root 2, these are two positions on the path at which kinetic energy and potential energy are equal. Now, see here, we have taken kinetic energy graph and potential energy graph with position. But we know kinetic energy is 1/2 m omega square x square and x is equal to a sine omega t plus phi. And if we take this, it will become, and velocity we know, velocity is a omega cos omega t plus phi. So kinetic energy is 1/2 mv square. So it is proportional to cos square omega t plus phi. While potential energy, it is proportional to sine square omega t plus phi. Now, sine omega t plus phi can be positive or negative. Cos omega t plus phi can be positive or negative. That's why velocity can be positive or negative. Negative means along negative direction. Positive means along positive direction. But here we have square of sine square and cos square. So kinetic energy and potential energy will always be positive, either zero or positive value. Similarly, kinetic energy, either zero or positive, and total energy is always positive. And we know negative kinetic energy is not possible. Now, so kinetic energy is proportional to cos square omega t plus phi, and potential energy is proportional to sin square omega t plus phi. So you can plot graph of kinetic energy with time as well as potential energy with time. So we'll plot that graphs. So here, first graph shows you position versus time now. And second graph shows you, I will show again. Second graph, this is second graph, this is first graph. First graph, it is position versus time, and corresponding, we know kinetic energy depends on position, potential energy depends on position, and we can find, so this graph, so see, this graph, it is for kinetic energy, and red graph is for potential energy with time. Now see here, this difference, it is 2 pi, and its time, it is t, periodic time t. If we take same 2 pi here, same 2 pi from this point to this point, see how many cycles for kinetic energy and how many cycles for potential energy. So see, for one position cycle, this means displacement versus time graph, one cycle, time required for one cycle, within that time, we have two cycles of kinetic energy. So kinetic energy also goes from, it goes from 0 to some maximum, again maximum to 0, 0 to maximum. So there are two cycles. This is first cycle of potential energy, and this is second cycle of potential energy. Similarly, this is first cycle of kinetic energy, this is first cycle, and this is second cycle of potential energy. Sorry, this is first cycle. These two gives you first cycle, and these two gives you second cycle. So for one position cycle, there are two cycles of kinetic energy or potential energy. Means two oscillations of energy, kinetic energy or potential energy for one oscillation of position. That's why we say that for one cycle of oscillation of particle, there are two cycles of kinetic energy and potential energy. So the frequency of kinetic energy and frequency of potential energy is twice. Because in one cycle, here we have two cycles in the same time. So on the basis of these discussions, we'll see some questions. Now I have taken small question. A particle executes SHM along x-axis at a certain instant. Its displacement is a by 2, and at that position acceleration is a0. What is the acceleration when the displacement becomes a by 2? So here means suppose particle is moving along straight line between plus a and minus a. Here a is amplitude, and we have taken position here a by 2. At a by 2, acceleration is a0 at a by 2. This is position, that is a by somewhere here. You will get a upon root 2. Somewhere here, a upon root 2. So what is acceleration at a upon root 2? How can we find? We know. acceleration d2x by dt square, it is minus omega square x. So if we take magnitude, d2x by dt square is proportional to x. Means acceleration is proportional to displacement. Now here displacement, first displacement, let us call that as x1. For this acceleration is a1, that is a0. So x1 is equal to a by 2 and acceleration a1 is equal to a0. Now we will take second position x2, that is a upon root 2. We have to find acceleration for that. What is acceleration? Now this is equation. A is proportional to x or x is proportional to a. So when x1, so I can take a1 is proportional to x1, a2 is proportional to x2. So simply take ratio. A1 upon a2 is equal to x1 upon x2. So a2 will be equal to a1 into x2 upon x1. So a2 will be, what is a1? A1 is a0. What is x2? X2 is a upon root 2 divided by a by 2. So simply calculate a2. So this 2 will go here. So we'll get a0 a 2 times upon root 2a. So it is now, if we calculate this, we'll get root 2, a will cancel, root 2 a0. So your answer will be root 2 into a0. This is acceleration at point, at position a upon root 2 from the equilibrium position if acceleration at a by 2 is a0. Now, next one. A particle performs SHM. Let T1 be the time taken to move from x is equal to 0 to a by 2 and T2 be the time taken to move from x is equal to a by 2 to x equal to a. Means here this is path of oscillation. This is equilibrium position. Here this is plus a and this is minus a. Minus a. So this is x equal to 0, x equal to plus a, x equal to minus a, and suppose we take a by 2. This is a by 2, x equal to a by 2. Now when oscillator, suppose this is oscillator, it is moving. And when it goes to this position, a by 2, it will take some time t1. Now from this, it will go up to this. It will take time t2. From a by 2 to a2. Then whether t1 equal to t2, t1 greater than t2 or t1 less than t2. What is possible here? Or fourth one depends on amplitude. Now time of oscillation never depends on amplitude of oscillations. So what happens here? We have to go for this. V is equal to omega under root a square minus x square. So if we take V here, I will take here capital A because here amplitude is taken as capital A. So this is root of a square minus x square. V is equal to omega root of a square minus x square. So at x is equal to 0, velocity is a omega plus or minus. Plus means along this, minus means along this. And at x is equal to plus a, velocity is 0. So when oscillator goes from equilibrium position to extreme position, its velocity goes on decreasing. So if we take 0 to a by 2 and a by 2 to a, if we see average velocity over this path, let us average is v1, and average velocity over this path, you will observe that v1 will be greater than v2. Because as we go away from equilibrium position, velocity goes on decreasing. So I have taken average velocity over distance a by 2 and next distance a by 2. So v1 will be greater than v2. And we know 0 to a by 2 and a by 2 to a, distance is same. But velocity over first distance is large as compared to second distance, and we know when velocity is more, less time is required to cover that distance. So you can say here T1 less time will be required as compared to T2. So T1 will be less than T2. So here C answer, in our case, it is correct. Now next, for particle in SHM, which graph is linear, always linear? X versus T, we know X is equal to A sine omega T plus phi, and we have seen graph. It is a sine graph with time T. If we take velocity is A omega cos omega T plus phi. So it is cosine graph. A versus X. Now we know acceleration is d2 x by dt square. And it is minus omega square x. So if we plot graph of X versus A, so A is proportional to X. So you'll get linear graph. So here between A and X, acceleration and position graph is linear. And we have seen kinetic energy graph. It is inverted parabola about X is equal to 0. So for this question, C is correct answer. Now, next one, a particle executes SHM such that its displacement is given by x is equal to a sine omega t plus pi by 6. At what time from t equal to 0 will the particle be at the mean position for the first time? For the first time. So what is that time? Now if we see x is equal to a sine omega t plus phi, this omega t plus phi is called phase of oscillations. It is called phase of oscillations. And phi is called epoch. Epoch. So at t is equal to 0, what is x? I will call that as x0 suppose. That is a sine phi. Here a sine pi by 6. Pi by 6. Pi by 6 means sine 30 degree. So here this is plus a and minus a. This is 0. So it will start from this. This is x0. So it will go like this and it will come here. And it will come at x is equal to 0. At x is equal to 0, first time, omega t plus phi will be 0 except t equal to 0. Omega t plus pi, sin omega t plus pi, it becomes 0 at x is equal to 0. And first time it will become 0 when omega t plus phi is equal to pi. So now omega t plus phi means pi by 6 is equal to pi. Here phi is pi by 6. So omega t is equal to pi minus pi by 6. So pi minus means 6 pi minus pi upon 6. So it is phi u pi by 6. This is omega t. So what is t? T is equal to phi u pi by 6 omega. This is the time in which particle will reach the mean position for the first time. For the first time. Now next one, a particle in SHM has acceleration at displacement x1 and a1 acceleration a1 at displacement x1 and a2 at displacement x2 is equal to 2 times x1. What is the ratio of a2 upon a1? And we know acceleration is proportional to position, only opposite to the position. So we take numerical value. So a1 upon a2 will be x1 upon x2. So second position, a1 upon a2, we have to find a2. So we will get a2 is equal to a1 into x2 upon x1. So a2 equal to a1 into what is x2? 2 times x1 upon x1. So it is 2a1. So since position become twice, acceleration will also become twice. So a2 upon a1, it is equal to 2. Now next one, the maximum velocity of a body in SHM is 0.25 meter per second and maximum acceleration is 0.75 meter per second square. The period of SHM is, we know period of SHM is t is equal to 2 pi upon omega or 2 pi under root m by k. Now what is given? Maximum velocity. What is Vmax? Vmax is equal to a omega. This is numerically a omega and that is at equilibrium position. We know acceleration is what? d2x by dt square is equal to minus omega square x. Numerically, is equal to omega square x. Now maximum acceleration, it is at x is equal to a. So maximum a max, maximum acceleration will be equal to omega square a and velocity max is equal to a omega. Now this is given 0.25 meter per second and omega square a is given, that is what? 0.75 meter per second square. So a is equal to 0.75 upon omega square and we know this is the equation. A omega is equal to 0.25. So I will use a here. So 0.75 upon omega square into omega is equal to 0.25. So 1 upon omega is equal to 0.25 upon 0.75. So it is what? 1/3. So 1 upon omega is 1/3. So T is equal to 2 pi upon 1 upon omega is 1/3, means 1/3. So 2 pi by 3 second. So it is 2 pi by 3 second. Now next, a particle executes SHM.
Excuse me, Samde sir. How many problems are remaining?
It's the last one.
Okay. Let's finish.
Okay. A particle executes SHM. Its velocities are v1 and v2 at displacements x1 and x2 from mean positions, respectively. The period of oscillation will be whether first one, second one, third one, or fourth one. This is period. So simply, if we see here, plus A and minus A, these are extreme positions. So suppose we take this first position x1 and second position x2. Here velocity is v1 and velocity is v2. These two are given. We have to find period of oscillation. How can we find? So we know v is equal to omega under root a square minus x square. So I can write v1 is equal to omega under root a square minus x1 square, and v2 is equal to omega under root a square minus x2 square. This is relation between these two. So if we square here, v1 square is equal to omega square a square minus x1 square, and v2 square is equal to omega square in bracket a square minus x2 square. So just this is equation first, this is equation second. Just subtract v1 square minus v2 square is equal to what? Omega square a square minus x1 square minus omega square a square minus x2 square. So if we see omega square a square will go, omega square a square will go, but here we'll get minus omega square x1 square, and here we'll get plus omega square x2 square. So we'll get omega square in bracket x2 square minus x1 square. So what is omega? Omega square is equal to v1 square minus v2 square upon x2 square minus x1 square. So what is omega? Root of v1 square minus v2 square upon x2 square minus x1 square, and t is equal to 2 pi upon omega. So take inverse of that. So we'll get what? This one, C. So this is the answer. So thanks very much.
Can we take some questions? If audience, some students have some questions related to this, they can raise hand and they can ask a question, if any. Otherwise, we'll directly go for this. Yeah. Sindhi sir.
Yes, sir.
Yeah. Please go for vote of thanks now.
No questions. We thank the today's speaker on behalf of IAPT SRC PUNE and Settle IAPT. I would like to thank the today's speaker, Professor P.S. Tambade sir. Sir has very meticulously and nicely explained all the basics of the oscillations, simple harmonic motions, and all types of the oscillations, conditions of the oscillations at different positions and different mathematical derivatives, mathematical formulations. Also, sir has taken the possible numericals for the NGP also. So I thank Professor P.S. Tambade sir for today's session, and also thank the audience, the participants who have joined this today's session and listened the this all the content very nicely. So I thank everyone for the your presence also. So on Monday, we'll be having a next session by Professor Dr. Gurashnath Gotesa. So he might be taking the classical mechanics problems. So with this, I end today's session. So thank you everyone for your attendance. Yes.
Thank you very much.
Thank you. Thank you all.
Yeah, thank you
Thank
so
you
much.
all for this. Okay.